Welcome to The Debate. Our discussion today plunges into what I think is a core tension in modern algorithm design: the relationship between these very practical, intuitive methods, the heuristics we use to solve daily problems, and the formal, structural rigor that comes from theoretical complexity analysis.
And this whole conversation really springs from a pretty powerful and, let's be honest, provocative assertion in our source material. The quote is, "Without learning to guide it, everything sinks into vulgar routine." Now that phrase, vulgar routine, is doing some heavy lifting there. It suggests that just intuition, just practice, if you leave it unchecked by formal theory, will inevitably fall apart into ad hoc, inefficient, and fundamentally flawed solutions.
And that framing sets the stakes perfectly, I think. We're really examining whether a deep theoretical understanding fundamentally elevates and perfects practical algorithm design. Does it provide essential tools, essential guarantees that intuition or just trial and error can never truly replicate? Is theory the only way out of that vulgar routine?
See, I come at it from a slightly different angle. I want to challenge that idea of fundamental necessity and asking whether robust, empirically tested heuristics, the kind you develop through rapid iteration, domain expertise, and local search, offer sufficient utility. Are they often faster, more accessible, and ultimately just adequate for the vast majority of real-world engineering challenges? Does that make the implementation cost of formal theory, quite frankly, overkill sometimes?
Well, I'm going to hold that theory is the indispensable compass and toolkit. It provides a layer of certainty, of provable quality, that transforms practice from an unverified craft into rigorous engineering and eventually science.
And I'll argue that practical, tailored heuristics frequently get you results that are good enough and they get you there quickly. The idea that they sink into vulgar routine suggests this guaranteed degradation, and I just see sufficient utility being achieved without the implementation debt of these really complex theoretical constructs.
Okay, so let's start with the most basic dilemma a practitioner faces. How do you know if you've found the best solution? Take a problem we see constantly in resource allocation: packing jobs to machines. The quick, intuitive heuristic is often just a simple, greedy approach. You assign the next job to the first available machine, or maybe the one with the least load. It feels pragmatic and, it seems to work.
Right. And that greedy rule works great, right up until the moment it fails catastrophically in an edge case, which is exactly why theory is so valued here.
Exactly. Without theory, we're just stuck with this unverified empirical performance. We might be leaving 20% of the possible efficiency on the table, and we would never even know it. But this is where theory immediately steps in. It identifies this challenge as a form of bipartite matching and definitively places it in Class P. And that classification it's transformative. It means an optimal, highly efficient solution using something like the network flow framework or, the Hopcroft-Karp algorithm is not only known, but provably polynomial time. We stop using guesswork, we implement the best known solution, and we move on. Theory provides the absolute certainty that the empirical approach just lacks.
I'll concede that theory provides the ultimate certainty here. I will. But I'm going to challenge the relevance of that optimal certainty for a lot of engineers. You presented a problem where the optimal solution is, okay, straightforwardly implementable because network flow is a well-established library tool. But what if the implementation overhead of that optimal solution, the setup, the data structure requirements, is significantly higher than that simple greedy rule? If the simple greedy rule gives me 99% of the optimal performance 99% of the time, and I can implement it in an afternoon versus spending 2 weeks integrating a sophisticated network flow solver, then pursuing that theoretical certainty, it just becomes academic. You're suggesting that anything less than optimal is vulgar routine, but engineering sufficiency often dictates that the fastest adequate solution wins the day. That certainty is overkill.
I see your point about implementation overhead, but I think that's more of a commentary on library development, not on the necessity of the theory itself. The theory allows the practitioner to stop searching for another heuristic. It provides the strategic knowledge to halt that experimentation process and just implement the best known method. That efficiency, all that saved time and experimentation, is invaluable.
Okay, but let's look at a scenario where theory doesn't deliver optimality, where it just sort of validates our intuition. Think about circuit partitioning, which is often modeled as the graph bisection problem. The intuitive approach here starts with robust local search, iteratively swapping nodes between partitions to reduce the cut size, the celebrated Kernighan-Lin or FM algorithm. Now, when you apply theory to graph bisection, it confirms what your intuition already suspected. The problem is NP-hard. So what happens next? The solution strategy shifts right back to investing heavily in robust heuristics and tuning that local search, which is precisely where the intuitive practitioners started. When theory hits that brick wall of NP hardness, its primary function is, it's negative. It merely validates the path we were already forced to take.
That's an interesting point, though I would frame it differently. I don't think theory just delivers negative news. It guides strategy. You called NP hardness a brick wall, but I see it as a map. This map prevents engineers from wasting months or even years trying to find an algorithm that optimally solves the problem in polynomial time, an algorithm that we can prove doesn't exist under current assumptions. This is an immense efficiency gain over pure trial and error. Theory instantly cuts through all the noise, and it tells us exactly where to focus our limited engineering budget, on robust heuristics, on approximation algorithms, or on the pursuit of tractable special cases. This systematic guidance, it transforms what would be fruitless labor into a structured investigation.
Okay, but let's stay on approximation algorithms for a moment, because this is where the theoretical cost really starts to escalate. Let's consider min-cost multi-net routing, a close cousin of the Steiner-Forest problem. This is an extremely challenging problem, confirmed to be NP-complete and even APX-hard. Crafting an intuitive heuristic here it's like throwing darts in the dark. You have no idea how bad your solution might actually be.
And this is precisely where theory demonstrates its unmatched value. Quality assurance through the guarantee. For Steiner-Forest, theory, specifically by using the powerful primal dual schema, provides a guaranteed 2 approximation.
Wait, slow down. For the listener who is focused on practical performance, what does knowing we have a 2 approximation practically guarantee? What does that buy me?
It is a profound level of quality control. It's a formal, provable bound that means the solution you derive, no matter the input data, no matter the specific network topology, will always be within 2 times the absolute optimal cost. If the absolute best path costs $100, your algorithm will never cost more than $200. This isn't empirical data, it's mathematical certainty. No custom ad hoc heuristic can ever claim that level of reliability without being grounded in that deep theory.
While that guarantee is incredibly strong intellectually, we have to weigh the complexity of implementing the primal dual schema itself against the practical cost. These methods often involve highly complex dual formulations, sophisticated data structures, and careful handling of constraints that are just far beyond the scope of an average development team working on a tight deadline. So, if a simpler, custom, field-tested heuristic, maybe a refined shortest path search, performs close to optimal 95% of the time, and empirically it delivers an average 2.1x or 2.2x approximation, the engineering choice, driven by deadlines and resource scarcity, is often going to favor the fast, accessible solution. A working solution, even one without published formal proof, is usually prioritized over the high-cost, guaranteed bound. You're selling a Ferrari engine when the client needs a durable pickup truck.
I'm just not convinced by that line of reasoning. You seem to be equating sufficiency with low effort. That gap, the one between unverified average performance and a formal guarantee, is what separates reliable systems from brittle ones. What happens when the input data changes? What happens when a rare non-average case appears? Your empirical solution breaks. The theoretically guaranteed solution holds. That robustness is the definition of quality engineering.
But the theory often leads us back to a complexity that is simply untenable for the scale of the problem.
Then you are missing the finesse that theory provides, which is often its most lucrative offering. Let's look at the ultimate cost of neglecting theory. The case of layout decomposition, which mathematically maps to the max cut problem. Generally, max cut is NP complete, another brick wall. A naive practitioner or one reliant only on intuition would correctly turn to heuristics or approximation algorithms, maybe using a generic relaxation technique that provides a guaranteed 1.38x approximation. They settle for good enough. But theory reveals a gold mine here. The specific constraints of circuit and chip layouts often mean the resulting graph structure is planar. And for the special case of planar graphs, theory reveals that max cut is actually polynomial time solvable.
Wow. Okay. That's a huge opportunity missed.
An absolute collapse of efficiency. Without the theoretical finesse, the awareness that we must search for structural properties like planarity, the generic heuristic gets implemented, and you completely overlook the possibility of obtaining the optimal solution, and quickly. Theory doesn't just guide strategy, it provides the intellectual lever to achieve elegance and optimality, where others just settle for brute force.
That's a compelling argument for the value of structure, but have you considered that the identification of a special case like planarity is often driven by real-world geometric constraints? Things you discover through iterative design, not just abstract complexity analysis. The engineer laying out the chip might observe through simple visual inspection or early design constraints that the connectivity matrix rarely, if ever, crosses lines. That practical observation is what suggests the underlying planarity. The best practitioners often identify those structural constraints through practice and deep domain knowledge, which mitigates the risk of missing the gold mine even before running a formal complexity check.
But that's relying on serendipity or, exceptional personal experience. Theory provides a systematic framework for actively searching for these hidden easinesses. It transforms that serendipity into a scientific process, ensuring that no stone is left unturned in the pursuit of the best known performance. That active search is precisely what prevents the routine from becoming vulgar. It's the systematic application of learning.
I'll concede that theory provides the most efficient language and systematic framework to exploit that structure once it is identified. My skepticism lies solely in the assertion that without the formal theoretical learning, practical effort inevitably sinks into inefficiency. Many engineering challenges are solved perfectly adequately by a talented team leveraging robust local search methods and greedy rules that are constantly refined based on empirical feedback. They rise to a level of engineering sufficiency without needing to become fluent in primal dual analysis.
But again, how do they define sufficient without a theoretical benchmark? They might achieve 99% of the optimum, or they might achieve 50%. That theoretical gap between unverified performance and a formal guarantee remains the chasm that separates inspired craft from rigorous, scalable engineering.
And that chasm, while it's intellectually significant, sometimes it exists in a space where the marginal utility of closing it simply does not justify the implementation cost or the required specialized knowledge. We are trading ultimate quality for immediate, adequate performance.
It seems we agree that the most powerful solutions emerge when learning systematically guides practice, even if we fundamentally disagree on the mandatory nature of implementing high-cost theoretical rigor in every single situation. To summarize my position, theory is far more than mere classification. It is a toolkit and a compass. It provides certainty for solvable problems, moving us beyond guesswork. It offers essential strategy for intractable ones, acting as a crucial map that halts futile searches. It delivers provable guarantees for quality, defining reliability. And finally, it provides the finesse to identify and exploit hidden easiness, ensuring we don't settle for good enough when optimality is within reach. This systematic elevation is mandatory to ensure practice avoids sinking into unverified performance and inefficiency.
And I remain unconvinced that all practical effort without formal theoretical analysis just sinks into vulgar routine. While theoretical frameworks offer undeniable clarity and powerful bounds, the operational reality of algorithm design often necessitates prioritizing accessible, fast, and robust heuristics, the very tools theory sometimes validates as the most practical path forward for NP-hard challenges. Intuition, when it's deeply informed by experience and tested empirically across a wide range of use cases, often yields sufficient utility without the full complexity of formal proofs.
Well, the source material deeply illuminates this tension between intellectual rigor and immediate utility, demonstrating that the pursuit of the best known solution is an ethical and engineering imperative.
Indeed. It suggests that while practice can yield sufficiency, The highest level of performance, reliability, and insight is achieved only when that formal learning is systematically applied to rigorously guide and critique the entire development process. There's clearly much more to explore in the interaction between complexity and accessibility.